This is a story about our eagles, one of the largest populations of scientists with PhDs in the Baltic states. With their eagle eyes, they're able to see the future, even in the very thinnest nanolayers that cover the surfaces of everyday household objects. In their fortress, which is officially called the Institute of Solid-State Physics of the University of Latvia, they have, in the space of half a year, developed around 50 scientific projects and more than 100 scientific publications. What unites them is a love of physics. Yeah, at first nothing's really clear. It's all so sterile, even a little austere. But let's take a closer look. Interesting. How many hard nuts has he already cracked today?
I work with electron paramagnetic resonance spectroscopy, and here we investigate the structure of solids. The main area of interest for me is point defects, which are formed after irradiation with X-rays or other forms of ionizing radiation. I conduct experimental measurements, study crystals by varying crystal position in respect to magnetic field. Thus, I obtain experimental data for which I carry out simulations, and from these results I can deduce the defects which are formed in the crystal structure.
In this fortress there are, for the most part, two kinds of scientists. Practitioners like Andris, who carry out experiments with real materials, and theorists, who are solely engaged in virtual experiments on their computers. Occasionally, though, we come across a third kind, a synthesis of these two types of scientists, the kind of super scientist that is Alexei.
Our field of research is related to X-ray absorption spectroscopy using synchrotron radiation. This is a nice technique which allows you to get information about atomic structure of different materials, from nanomaterials till bulk materials.
In fact, the synchrotron's X-rays allow scientists to study any material at the atomic or nano level. And moreover, the high power of the radiation used means it can be done in a short period of time and at high quality. This is how Alexei can test any of his theories in practice and improve the results of the experiment without delay. The model is changed until the desired result is achieved. He is obsessed with synchrotrons.
The most interesting part of our research is, of course, related to the use of these large-scale facilities, synchrotrons, because this equipment is not available in most laboratories around the world. And when we are able to get access to synchrotrons, we are able to work at the same level as the most famous labs in the world.
Life in the Institute of Solid-State Physics is not always so smooth. Occasionally, events are only solved with the tension characteristic of detective work.
Here in Institute, we are producing organic light-emitting diodes. Basically, we are investigating new organic materials which could emit light. And it's quite a strict procedure how we make these OLEDs, yes. But at the same time, we had one accident where we prepare the same OLEDs with exactly the same structure. And in the second time, we couldn't manage to get OLED. We couldn't get out the light.
What had happened during this time? Had the technical condition of the equipment changed? Had there been a change in the people involved in the project? What about the ambient temperature? Instead of the previously smooth nanolayer, we saw the appearance of a rough and uneven surface. Together with his colleagues, Ivers analysed all of the steps of the experiments and so followed a conclusion worthy of Dr. Watson himself.
The main problem was that one experiment was done in the summer, one in the winter. And in the winter, we have a quite dry air in the rooms, yes? And if we have dry air, then electrostatics is more effective, I would say, yes.
This kind of electrostatic phenomenon can be seen on a cold winter's day when there is only a little moisture in the atmosphere. This is because water is one of the best carriers of static charge. In the summer, however, the air contains more moisture, and that prevents the substance from fully charging. The first experiment was carried out in the summer, but was repeated in the autumn when the rooms were already being heated, and as a result, the air in them was drier. It was then the scientists finally caught sight of the light at the end of the diode.
We increase humidity in the room, and all went in a correct way. And we again got very good OLEDs. Yeah, sometimes it's crazy.
Those who search find, and not always what they were looking for. And so it is with copper. This metal has found a way of penetrating the tungsten trioxide layer and making it antiseptic. Martins and his colleagues originally studied the thin layers in order to change their transparency. But in the end, they discovered how to make them antiseptic.
In this particular research, we tried to develop optoelectronic layers, which, for example, could be used in smart windows applications. Well, when the pandemic starts in the world, we had an idea that maybe our coatings could do damage on microorganisms.
It could be used, for example, on an ATM keypad or to coat door handles, because the copper ion is able to pierce the cell membrane of the bacteria, thereby causing it to die.
Well, because we know our material, we know of which compounds it consists, and well, in principle, we can explain how it could work. And we did tests, and for not actually large surprise, it actually worked.
When a job has been completed, it's time for cake. Although none of the people working here know a recipe that is guaranteed to result in discoveries or new technologies, they can certainly discuss cake recipes during their tea break. We have only scratched the very thinnest layer of what goes on here from day to day. These are the people at the Institute of Solid-State Physics at the University of Latvia. Theorists and practitioners, dreamers and realists, but all in all, creative and with a love of life. Maybe one day you'll be one of them too.